Titrate 10.0 milliliters of an ammonia solution of unknown concentration with 15.0 milliliters of a 0.1 molar HCl solution to the equivalence point. The question is, what was the concentration of the ammonia solution and the pH at the equivalence point? And we're also given, it says, note, the base dissociation constant is 1.8 times 10 to the minus 5 for ammonia. That is a base. Okay, let's go ahead and deconstruct this problem. All right, so we have 10.0 milliliters of an ammonia solution. We don't know the concentration. And we're titrating that with 15.0 milliliters of 0.1 molar HCl to the equivalence point. They're asking us for the concentration of ammonia of the starting solution and the pH at the equivalence point. We're also given the Kb for ammonia. Okay, so with that information, we're going to go ahead and identify what we're looking for, and then break that down into all of the information that we have, and go ahead and figure out how to solve this. So the question is telling us that we need to find X, where X is the molarity of the ammonia solution. And then we need to find, after that, the pH at the equivalence point. Okay, so we'll do one before the other. We'll find out the concentration, the unknown concentration of the ammonia solution that we started with. Let's go ahead and organize all of our information. This first part is where you write your objective, your goal. The second part is where you write your information, basically all of the other pertinent information. And this is just a problem-solving framework that I use for pretty much everything that in my life that's complex. So it's math problems, chemistry problems, pretty much anything like that. So all of the information that we have, let's organize that in a way that makes sense to us. So I see titration and I see adding one thing to another. So what I'm going to do is I'm going to actually write this sort of in a sort of a sequential way. So the first thing that we have is the analyte solution, and that's the ammonia, aqueous. And so we can draw a little figure just to help us keep track of all of the information and how it's structured. Okay, so the light blue just represents all the water in the background. You do have water molecules. And now let's go ahead and draw a legend where orange represents ammonia and green represents hydrogen atom. So if we draw an ammonia molecule, it's going to look something like this. And a nitrogen atom surrounded by 1, 2, 3 hydrogen atoms. We can go ahead and copy paste this guy, copy, and we can put a few of them inside just to indicate that we have these things floating around in solution. And we'll put 5 there. Okay, delete that one. That is the analyte. Now, to that, problem's telling us that we are adding a certain amount of the titrant, the thing that's going to titrate. The titrant. And the titrant is HCl aqueous. And that one we can draw a similar picture. And we have, actually, before we move on to that, let's go ahead and write down the rest of the information relating to the starting ammonia solution. It says we have 10.0 molar, or 10.0 mLs, milliliters, and we don't know the molarity. We don't know the concentration. Okay, so, and we also know we can go ahead and write down the Kb. Since the ammonia is over here, we can just write the Kb beneath this for ammonia. The Kb, or the base dissociation constant, is 1.8 times 10 to the minus 5 power. Now let's go back up and continue where we were going. The titrant is the HCl, and I'm going to make this beaker a little bit bigger. Whoops. And it will also have water. And similarly, we should also choose some atom color coding to put the molecules of HCl in. So let's keep the hydrogen atom green, and let's give chlorine a purple circle. Okay. Now, actually, I should also note that each one of these representations represents the initial state before any equilibrium or reaction with water occurs. It's sort of just this hypothetical situation where you just add ammonia to water and you don't let it react yet. And I'll go into why we want to do that. And similarly here, this is just initially, just as you add, if you had pure HCl and you add that to water, before anything happens to that HCl. So, all right, HCl is just one Cl atom and one bonded to one hydrogen atom. And we can put, let's say we put 5 of these in here as well. 1, 2, 3, 4, and 5. Okay. And then delete that guy. Now, it says we add enough titrant in order to reach the equivalence point. So we go to the equivalence point. And actually, before we do that, we should add the rest of the information for the HCl. We have 15 mLs of 0.1 molar HCl. So we can write that down. We have 15.0 mLs. In this case, we do know the concentration of the titrant. That is 0.1 molar HCl. Okay. And the K, the Ka, I could write the Ka for HCl. It's actually not known experimentally because it's so large, because it's a strong acid. So it's something like infinity, if you wanted to, know anything about limits in calculus. You can just treat it as like infinite. All right, so when we add the titrant to the analyte solution, we're going to get the fully titrated solution at the quote-unquote equivalence point. So let's go ahead and draw that. And notice we're going to get the addition of those two volumes since we're going to add these together. I mean, in principle, what you're doing is you're dripping it in drop by drop, and at the equivalence point, there's going to be some color change. We're actually not concerned about what happens up to that point. All we care about is really the starting point and the very end point. However, experimentally, you would be dripping the titrant into the analyte until you reach the final point. But since we know, whatever color it turns at a certain point, we know exactly how many drops we added. We added 15 milliliters of that. But we don't need to consider each drip. So let's make an even bigger container to represent the solution at the equivalence point. Okay. And now for this one, I'm not going to draw all the molecules. We'll just write this is at the equivalence point. Okay. And so I'm going to go ahead, now that I believe we have all of the information from the word problem down on paper, we have separated the objective, the two objectives up top, which I will go ahead and circle in purple. Well, in reality, we're just looking for X. And then the second one, we're looking for the pH at the equivalence point. And then we have a bunch of related information. So we have, I'm just going to go ahead and circle in, let's say, green, each one of these pieces of information. And this is sort of a lumped, there's a lot of lumped information here. But generally, you know something about the analyte solution. You know the volume of it. You don't quite know the concentration. That's what we're looking for. In fact, I'll go ahead and circle this purple just to identify that as that's what we need to find. And you have information about the titrant solution, which we've now organized. In addition, we know we're sort of structurally adding these two pieces of information together to get the overall thing, and that is at the equivalence point. Okay. So basically, with the structure of the way that I've set this up, we have three general groupings of pieces of information. We have to know what equivalence point means. We have to know how to deal with the 15 milliliters of HCl and 0.1 molar. We have to know that's a strong acid and that Ka is basically treated as infinity. The analyte solution, the ammonia, we know we have 10 milliliters. We need to find the concentration, and we know this Kb value, this base dissociation constant, and we will probably need to use that later on. So now that we have all of our information written down, we can go ahead and start solving this. So the third bullet point is always, give myself a little bit more room to write here, is where you're going to write down your strategy and execute, basically carry out whatever strategy you came up with. Now, for this particular problem, you'll notice I sort of go through a mind map, and this is to just give you an idea of how I think and how things are related and how I jump from one piece of information to the next related piece of information. So let's go ahead and start that. And the point at which I'm going to start is actually with this piece of information here. Or rather, let's take a step back and just talk about how I look at these things. So the first thing that we're going to try to find is X. So that thing up there. That's our objective. So that's our thing that we keep our eye fixated on. And then we sort of scan the landscape of the pieces of information that we're given. And this was also, in my mind, I also sort of helped you out and structured it in this visual way. But we have three general pieces of information. We have the analyte with some information over here. We have the titrant. We're going to add those together, and we're going to get something, and we have to know something about the equivalence point. So for this particular one, I'm actually going to start, in my mind, with this piece of information, the equivalence point. I could have started anywhere I wanted, but I just want to show you one way. You can choose to start wherever seems like makes sense or wherever you know information related to it. I'm going to start at the definition of the equivalence point. So you need to know what all these things mean. So the equivalence point in this context is when, so here I'm going to write the next thing it's related to is, well, the definition of the equivalence point. So it's basically when the titrant, which is HCl, or I should write when the active component of the titrant, I'll talk about what that active member is and hopefully should become clear in a couple of steps. When the active component of the titrant, not the titrate, titrant, fully consumes the analyte. And in this case, the analyte is ammonia aqueous. Okay, in that solution. Okay, so when the active component of the titrant fully consumes the analyte, now we have to think about where can we go from here? So if the active component of the titrant fully consumes the analyte, the way I think about this is, well, I know it's a titration, and a titration is basically where the titrant, you're just using the titrant in order to count atoms or molecules of the analyte. You're just literally counting how many ammonias you have in solution. Obviously, in chemistry, you use moles, but moles at the end of the day is just a number. It just represents the number of thing that you're talking about. So given that, we probably need to know the number of titrant molecules, or in this case, the number of moles of the HCl. So what we're going to do, we're going to split this up into two sides. And so over here, I'm going to figure out the number of moles of the titrant, which again is HCl, that we added up to the equivalence point. So the total number of moles of HCl that we added. So after we do that, then we're going to do the same thing except for the number of moles of ammonia. So we're going to find at least an expression for the moles of the analyte ammonia. Okay. All right, so let's do that. Let's come up with some expressions for both of these sides. And if you want to just a quick glance of the high level stuff again real quick before we start, take a moment and just look at that. Okay, let's go ahead and get started. Let's calculate the number of moles of the titrant HCl added up to the equivalence point. So if we look at this diagram over here on the right, the titrant, well, if we have 15 mLs and we have a concentration, we can calculate not the number of molecules, but we can calculate the number, well, we can calculate more directly the number of moles of HCl. And the way that we do that is through the definition of molarity, which is just the number of moles of that thing divided by liters. And so this, I'm assuming that you're pretty familiar with this, since usually you do a lot of these practice problems. So we're going to convert 15.0 milliliters into liters, and then multiply that by the molarity of HCl in order to get the number of moles of HCl. Let's do that. 0.0150 liters, that's just 15 milliliters converted to liters. Just divided that number by 1,000 to get liters. And then we have our concentration, 0.1 molar HCl. And so we get 0.00, just write it on the next line here, 0.0015 moles of HCl. Okay. So let's do the same thing for the right side here. So we have in the analyte, we have 10.0 milliliters and X molarity or molar of ammonia. So we're going to have a variable here, but that's okay. So we have convert 10.0 milliliters to liters, 0.0100 liters, and times X molar. And so we get, make sure that we did that correctly. Yep. Okay, and so we get 0.0100x moles of ammonia. Okay, so that has a variable in it, but that's okay. Let's go ahead and continue on the HCl side. Now, what we're going to do is we're going to say, I know that we're going to add this to this, or vice versa, but it doesn't matter in the end. And we're going to get some solution that has the total volume. I'll just write the total volume here. The total volume. But what we're going to do is we're going to do this hypothetical step where we add all this. We're basically just throwing in all the stuff all together, and we're considering, well, what does the ammonia look like in that volume, assuming that none of the HCl is added to it. Even though it is there, we're basically just looking at what happens to the ammonia at the very instant that we add it to the entire volume, which represents the final endpoint, equivalent point. So let's consider that, or rather in this case, the HCl, sorry. So we're considering the HCl alone aside from the ammonia, but in the entire volume. So let's make a little drawing of that. And so we have, well, we can just use the same one that we have up here. We have the HCl. Okay, copy paste that. Erase that since we already have one. Okay. Now I know I copy pasted, but really the volume is larger. So the volume is 25.0 milliliters. So it's larger than this 15 because we're adding both the solutions together. We're just considering what's the effect of what type of reaction or equilibration can we consider just for the HCl and water, but in the entire volume. So in order to do that, well, we have the number of moles of HCl, and we have the new volume. We have the new volume. And we say, okay, what we're going to do is we're going to equilibrate the HCl and the water alone first. Okay. And so initially, what do we have? Well, initially the concentration of HCl, well, that's just, we have the number of moles. The number of moles of HCl is not going to change if we add water and we add ammonia. So we're going to have 0.0015 moles of HCl divided by the total volume of the solution at the very end of the experiment at the equivalence point. So divided by 25 milliliters, or in liters, that's 0.0250 liters. And so that becomes 0.060. 0.060 molar HCl. Okay. All right. So now that we have the molarity of HCl at the very beginning, we can now consider what's going on. So in the solution, we have HCl to begin with. We know the concentration at the start. And what's going to be useful in your career or as a chemistry student is when you're given a lot of things that could react together, you need a systematic way to discern what things are important and what types of reactions are going to occur. So here's what I do. The first thing that I do is I identify the major species in the solution. And by this, I just mean the chemicals that are in the highest concentrations. And so from the diagram above, you see, well, the blue hash marks just represent lots and lots of water molecules. I know I'm not drawing them, but they're water molecules. So one of the major chemical species is water. And it's approximately, I'm not going to derive this, 56 molar. And that, I'll just give you an idea, that comes from the density of water. Convert grams to moles and you get the molarity. So I encourage you to do that if you haven't done that yet for determining the molarity of pure water, liquid water. The other component that's in the majority is going to be HCl. HCl, and its concentration is 0.060. That's what we just calculated above. Now, the minor species, I'll just put this in brackets. It is still important, but it's important to understand because they're really still there. It's just that from a calculation standpoint, we don't really care that much about them because their concentrations are so small. So the minor species are OH minus, which are approximately 10 to the minus 7 molar, and H plus, which is also approximately 10 to the minus 7 molar. You might ask, where do these come from? Well, this just comes from the dissociation of water. So this just comes from pure water of 56 molar. When it equilibrates with itself, it's going to split apart into H plus and OH, but only to an extremely small extent. And 10 to the minus 7 and 10 to the minus 7 molar for both OH minus and H plus. Those compared to these other concentrations are basically like comparing, you have $1 billion, I'm going to take away or give you $1 single, and your most reasonable answer will be, I don't care that much. So that's basically what we're doing here. We just don't care that much about those, and we're just going to consider those to be roughly 0 compared to the other ones. All right. Now, the next thing that we do, now that we've identified the major species, water and HCl, we have to identify the possible reactions involving the major species. Okay, so now the possible reactions, well, we have water and we have HCl. Let's first write the reaction with HCl. When you throw HCl in water, HCl is an acid. So an acid is one which gives up a proton, and whatever is left behind is the product. And so the only thing that can take that proton is water. So we're going to write that first reaction, reaction 1, as HCl aqueous. It's going to split up into H plus and Cl minus. Okay. And we should also write for these reactions, since we're going to need to decipher between the major reaction, or between the reactions, which one is the most important. Well, importance is determined by the equilibrium constant, because we already know we have this component. But the question is, how much of this will be produced? And so that's given by the Ka. And the Ka for HCl, it's a strong acid. So it's just, as I said before, it's much, much greater than 1, or one might think about it as being approximately infinity. So essentially, all of the HCl in solution is just going to turn into H plus and Cl minus. But let's just go through systematically, just so we can see the comparison with other reversible reactions, and to just show you that they can be treated the same way as long as you think about it carefully. Well, actually, sorry, let's go and write down the second reaction. So the second possible reaction, if we have water and HCl, well, water by itself dissociates. Not very much, but it does this. Liquid water can dissociate into H plus, aqueous, plus OH minus, aqueous. And the equilibrium constant that describes how many of the H pluses and the OHs there are versus waters, well, that's given by the Kw for water, and that is 10 to the minus 14. Notice that is a really, really tiny number. So basically, there's none of that's made. And so what we do now is we identify which reaction relating to these two things, we're asking what's going to happen when HCl and water mix. Well, the one at the top is going to be the major reaction because it has a K that's much, much larger than the other reaction. That's how we decide between the reactions. So that is the primary driver for this reaction, for this equilibration. HCl plus water, well, this reaction up on the top, number 1, is going to be the most important one to consider. Now, let's go ahead and consider that. So when we have a reaction, and in principle, we can just consider it like a reversible reaction, even though I've told you it isn't, but I want to tell you how to think about this so you don't have to have so much, you don't have to remember so many things. So let's rewrite the reaction, HCl aqueous. I'm going to split up into H plus Cl minus. And as I've said, the K is infinite, or much, much larger than 1. So if you just consider this as a reversible reaction, we go ahead and do our ICE table to determine what we start with, how much we're going to shift it from a variable, and what we're going to get at equilibrium, which at the end of the day, that's what we're looking for anyway. We're looking to see what is the split between products and reactants at that particular condition. So HCl, the initial concentration, I should write that everything in this table is in molarity. The initial concentration, well, we calculated that. That's 0.060 for HCl. We write 0.060. And H plus, we don't have any of that, or we rather assume that it's 0 compared to 0.060. 10 to the minus 7 is like a million times smaller than that. So from the perspective of 0.060, it's essentially 0. And Cl minus is in fact 0. We didn't allow that HCl to split up yet. Now we define a change. Well, this is the only one with anything in it, so the only place for this reaction to go is to the right. So we're going to subtract. We're not going to use x because we already have that variable. Instead, we're going to use y. So if we eliminate y from that side, if we subtract y, and all of our stoichiometric ratios for this reaction are 1 to 1 to 1, then if we subtract y from that side, we consume y molecules of HCl, we're going to produce y molecules of H plus and y molecules of Cl minus. And at equilibrium, we're going to have 0.060 minus y. We're going to have y there and y there. Now we can write the equilibrium constant for HCl. And you wouldn't find this on a chart. There's a reason for that, because it's too large to measure experimentally. So this is essentially like saying this is approximately positive infinity. And we're setting that equal to the law of mass action for this equilibrium constant. So we're writing the equilibrium expression. That's what that means. So we have the concentration of H plus, which is represented by the variable y, times y, which is the concentration of Cl minus. So we just square that, divided by the concentration of HCl at equilibrium. And the expression for that, algebraically, is this. Now, if you think about this for a little while, if you've taken limits in pre-calculus, this should be pretty easy. Or if you just think about, if this Ka is really large, it just means that the products are so heavily favored that effectively everything goes to the right. So what that means is that y, well, physically and sort of common sense wise, y must be 0.060 molar. And if that is the concentration of H plus, and that is also the concentration of Cl minus, since the expressions are the same. That's y. And also mathematically, if we plug 0.060 in for y, we get 0 in a denominator. Whenever we have a number in the numerator and a 0 in the denominator, that's effectively infinite, or not a number. So both in the mathematical way and the physical common sense way, that makes sense. And so from now on, whenever you have a reaction that has a K that's so large, so if you have like a strong base or strong acid, or something like that, you just treat it as it goes to completion, just like in the beginning of chemistry. You just treat it like a limiting reactant problem, or one that just has an arrow that goes all the way to the right. So in that case, you just subtract off 0.060 from that side, and you add 0.060 to both of the right sides. And so that's how you can do that from now on. But I did want to give you some grounding and to show that there's nothing really different about a strong acid. It just makes it a little bit easier to solve. And so that is giving us the H plus concentration, which we can use after that. Let's go ahead and do the same treatment for the base now. So let's remember what we did. We took the titrant, which is the HCl, and we equilibrated that but in the larger volume at the end. Now let's do the same thing for ammonia. We're going to allow all the moles of the ammonia from the starting analyte solution to equilibrate in the larger volume that represents the total volume at the equivalence point. And so for that one, we're going to also take that same picture. Okay, we're going to put it right here. Okay. So we take the number of moles. I know we have a variable here, but we'll be able to handle that shortly. And then we also note that the total volume is 25.0 milliliters, just as over in the left. And in this case, we're going to consider separately the equilibration. So we're going to equilibrate ammonia and water. And you're thinking forward, we are going to eventually allow the HCl and the ammonia to equilibrate. But I want to give you a more holistic view of what's going on and how to think about this in a sequential way. So initially, well, what do we have? We have 0.0100x moles of ammonia. So 0.0100x moles of ammonia. And the volume in which it's sitting, in which those molecules are sitting, well, that's 0.0250 liters. And so that equals 0.400x molar ammonia. Okay, so the initial concentration of ammonia is 0.400 times x, which x is the concentration of the original analyte solution in only 10 mLs. So now we have that. I'll go ahead and circle that, similar to over on the HCl side. Now at this point, we can go ahead and identify the major species, just as we did on the left side. So when we have ammonia and water, the major species, as you might expect, are just ammonia, which has 0.400x molar, and water, which we already determined has approximately 56 molar for its concentration. Now the minor species. Now these don't come into play, but it just gives you an idea of to know that these things are present. It's just that they don't really matter because they're such small concentrations. So we also have, in this case, similarly to over on the left, we have OH minus of about 10 to the minus 7 molar, and also similarly H plus at approximately 10 to the minus 7 molar as well. And again, those come from the auto dissociation of water that's also present in just pure water. So those are effectively not going to matter because we're going to anticipate that this concentration of ammonia it's not going to be that small. It's going to be on the order of 0.1 or 0.01 molar, most likely. And if it isn't, then we would have to come back and consider the minor species. But for your level of chemistry, most likely you can always just ignore those. Anyway, the next thing to consider are the reactions. The reactions, let me just make this a little bit bigger. See it a little bit easier. The reactions involving the major species. Okay, so let's do similar things to the left side. So if we have ammonia and we have water, well, one reaction where ammonia reacts with water is just going to be effectively not really base dissociation in this case, it's really a base protonation reaction. You have ammonia, aqueous, plus water, which is liquid, and that's going to equilibrate with the product side. The ammonia is going to rip off a proton from the water because ammonia is a base. Ammonia is going to become the ammonium ion, which is now the conjugate acid of the base ammonia, aqueous, plus the conjugate base of the water that's acting as an acid on the left is OH minus. That is the conjugate base. Okay, so that is one of those reactions. And the K value, we also know. This is the definition of the base dissociation, or if you don't have a base with, as a salt, which you might be used to seeing, like NaOH, where it actually just dissociates. Other things that don't, where it's not that obvious, it's better to consider the reaction as like a base protonation reaction. So you're adding a proton or an H plus to whatever you're starting with. That is exactly this reaction, and the Kb value for ammonia, the base, is just 1.8 times 10 to the minus 5. Okay, so the second reaction is going to be the same as what we have on the left. Since we do have water, liquid is going to equilibrate with H plus and OH minus. And you might be thinking, well, do we consider that? Well, in this case, it's not going to be necessary because the concentrations of everything else is so much bigger. The Kw for this reaction is, again, 10 to the minus 14. And again, in this case, if we're allowing the ammonia and water to equilibrate, we're considering that, we need to consider both the major species, which we've identified as ammonia and water, and also the major reaction involving those major species. Now, this one is going to be the major reaction. Why, might you ask? Well, remember, the major reaction is the one that has the highest K value, because we're asking which one is the most important one. Well, the most important one is the one with the higher K value. 1.8 times 10 to the minus 5 is roughly 9 orders of magnitude greater than the dissociation of water, or 1 billion. It will produce 1 billion times the products as the second reaction will, and therefore the top reaction is the reaction that drives this process, and that's the one that we choose. So let's go ahead and execute that. We are going to write the reaction that we have, similar to on the left. So we have ammonia, aqueous, plus water, liquid, is going to equilibrate with the ammonium ion plus the hydroxyl ion. And we already know the Kb. I'm not going to write that again. And we're going to do our ice table, which is just to say that we know the initial concentration, so we're trying to find the equilibrium concentrations of all these things, just using a simple algebraic variable, and we know that all of the concentrations are related through the stoichiometry. So we only need one variable. In this case, the initial concentration of ammonia is 0.400. Let me just add a little bit more room here. 0.400x. And the water column, since that's a liquid, that will not come into play in terms of the equilibrium, because any pure water, pure liquid, or pure solid will not come into play. So ammonia at the beginning is 0, and OH similarly is approximately 0, since it's like 10 to the minus 7 at the beginning, but we just consider that 0. Similarly with the HCl. The next thing to do is to identify how much we're going to shift it. Well, again, we start with this side. The only way to go is to the right. So we need to subtract off some variable that represents how much of the ammonia we don't know that number. So let's define a variable, and since we've already used x and y, I'm going to use z. So subtract z. Now through the stoichiometry, we have 1 to 1 to 1 to 1. So if we consume z molecules of ammonia, that means by the stoichiometry, by the ratios or the proportions, we need to produce z molecules of ammonium ion and z molecules of OH minus. At equilibrium, we have 0.400x minus z as the equilibrium concentration expression for ammonia. For ammonium ion, we have just z, and for the OH minus ion, similarly, we have z. Now let's go ahead and write down the equilibrium constant Kb for this for ammonia, which we were given. It's 1.8 times 10 to the minus 5. And now we can write the law of mass action, or the equilibrium expression for this equilibrium constant. We have the ammonium ion concentration, which is just Z, times the OH minus concentration, which is just Z, so we have Z squared, divided by the concentration of ammonia. And that expression is 0.400x minus Z. So this seems complicated, and actually it is a little bit, but I'll explain in just a moment how to make this simpler and to basically sidestep doing this particular part. But we are going to, if we did want to solve the quadratic equation in z, where x was just a variable, we would get z is equal to some function of x. We're not going to solve that. Well, instead what we're going to do is we're going to recognize the following. We're going to anticipate that, okay, after we equilibrate these things, we have the concentration of H+, we have the concentration of the ammonium ion, which is just represented, well, this is represented by this guy. It's also equal to the concentration of OH minus. And when we add these two things together, we know we're going to get the final thing here. And we need to get to the equivalence point. So that's when the active component, which we've already identified as the H+, that's the thing that becomes the acid once HCl is thrown into water, of the titrant fully consumes the analyte. So really the reaction that we need to consider next is the following. H+, well, there's two different perspectives. Okay, so in this case, we're still going to have a certain amount of ammonia, and that's a base. And since we're looking at the titration reaction, whenever you have acids and bases, it's always a neutralization reaction. We know that H+ is the active component of the HCl, so we're going to actually write two different reactions, because when we add the H+, the first thing that happens, the easiest base to protonate is going to be some of the OH minus. And this reaction goes to completion because both of these are very strong acids, which just means that the equilibrium constant overall is heavily or severely shifted towards the right. And you might recognize this. This is just the reciprocal of 10 to the minus 14, which is 10 to the 14th power. That's a ridiculously large number. So the H+ will fully consume all of the OH minus. That will happen first. And then second, then there's still H pluses left. All of the H pluses will then consume, you may have guessed it, we need to have another base. Well, the easiest base to consume after that is going to be the rest of the ammonia. And so that's going to produce NH4 plus. It's aqueous, 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 and that's also aqueous. And so the overall effect of, and let me just say, this reaction, since in the titration we're counting atoms, so even though the equilibrium here for NH3, or if we consider the reverse process, the acid dissociation of ammonium ion, it's still considered it's a very, very, very weak acid. So there's still going to be some of this left if we allow it to equilibrate, but not to the extent that we care when we're just counting atoms. So it's like saying, I'm using H plus and I'm using a billion H pluses, and I'm going to consume a billion and one H pluses. I don't really care if it's a billion one or a billion, it's still roughly a billion. So that last little tiny little bit we don't really care about. And so we're going to first consider this as a reaction that goes to completion. So the long and the short of it is that this entire process here was really unnecessary, because if you consider, let's consider the following. Let's say at the end of the day you're titrating H plus to count how many ammonias you have. Whether you have ammonia or ammonium ion, it doesn't really matter, because if you have one ammonium ion, you also have one OH from this reaction here. So in terms of counting, it's not going to change the amount of H pluses that you need to consume all of the base anyway. So let me just give you an example. If you have ammonia, you have a bunch of ammonia, and let's say we have 10 ammonias. And we can copy paste that guy. Copy and paste. So we have 10 ammonias. Now in the case that we just did, let's say in the process of producing some OH, we eliminated, I don't know, we consumed 2 NH3s. We consumed 2 of those. And what we produced was actually 2 OHs in its stead, let's say. So overall, we still need 10 H pluses to react with all of the ammonia, or all of the base that's there. Actually, let's just do it this way so it seems more obvious. So the 2 H pluses over here are going to react with the OHs first, and then all of the leftover ammonia is going to react with each one of the H pluses. So the fact that we considered this equilibrium up here on the top right, it didn't really matter, because at the end of the day, if some of the ammonia was converted to OH, the H pluses still consumed them, and it's as if just the H pluses were consuming all pure ammonia. So the other way that I would write this is just to say, let's see if I have that still in my, perfect. So you can consider this in 2 different ways. The first way, which is more complicated, or you can just consider it this way. Before, we don't allow any of this equilibration to occur, because we know it's whatever we produce, whatever base we produce is just going to be consumed atom by atom by the H pluses anyway. We can just do this. Instead, all of the H pluses consume all of the ammonia. So one by one, each of the H pluses consumes all of the ammonia. Okay, so really what we can do, we can just do that. And so that's our next step. And so in this case, instead of what we do is we just say eliminate this equilibration, and we just say instead we have 0.400x molar of ammonia combined with the equilibrated HCl, which breaks down into Cl minus and H plus. So the next step is then writing the total volume, which is still 25.0 milliliters. And instead, so inside of here, we have our major species, which let's remember what those were. So purple was Cl, orange was N. So purple was Cl. So we're going to have, it's a bit big, we have some Cl minus. And so let's draw some Cl minuses. Let's draw 5 of them. And we also have orange, which is going to represent the nitrogen atom, and the green, which represents the hydrogen. The green, which represents the hydrogen. And so we can draw N and then H, H, H. And so we can draw these by copy pasting here. And we'll put 5 of them as well. And what do we also have? Well, we also have just H plus ions. So the green, I'm not going to distinguish between plus or neutral. I'll just say plus or neutral. And so the green guys, we should put 5 of those as well. Since we no longer have HCl, we just have what's left after we split them all 5 of the HCls. So we have 5 chloride ions and 5 hydrogen plus ions. Okay, so this is what we currently have. And what we're going to do now is we're going to let's see, let me just make this a bit bigger. We're going to equilibrate the H plus, the Cl minus, what we're really doing is just H plus and ammonia. And the reason we're doing that, as we said before, is the effect is the same, whether you allow the ammonia to equilibrate or not. At the end of the day, we're just counting the number of ammonia species, whether it's ammonia or ammonium ion. So we'll do it that way. And so, as before, we identify what we have initially, and we currently have how much H plus? 0.06. So H plus, we have 0.060 molar of that. We have, what else do we have? We have an initial concentration of ammonia of 0.400x molarity. And then the water concentration. We know the chloride ion concentration actually isn't going to come into play. So, and I will show you why. I mean, we could go through, let's see, let's identify the major species. The major species in this case are H plus, Cl minus, ammonia, and water. Water is 56 molar, ammonia is 0.400x molar, H plus is 0.060 molar, and Cl minus is 0.060 molar. And similarly, in this case, the minor species, as I alluded to, I know we assumed that none of the ammonia dissociated, but I'm just showing in principle there is going to be a little bit of the ammonium ion. So I'll just write that. That would be a minor species. And then the other one is the OH minus, and that's really, really tiny. Okay, put that in brackets. Those ones don't really matter. They're effectively 0. And the reaction that's going to, the reaction between these two things, we could write all the reactions. Let's just do that for completeness. Reactions involving major species. Let's do that. Let's do, we have ammonia aqueous plus H plus aqueous is going to go to ammonium ion. And the next thing that we do is, so we can write another reaction. So that can be the first reaction. Another reaction, since the major species we have, let's see, we have water as well. And actually the equilibrium expression for this reaction is going to be, if I were to write the Ka for instead the ammonium ion, since that's the acid, that would be, I'm not going to derive this for you, but it's the Kw divided by the Kb for the conjugate base, which is ammonia, which is what we know. And that's approximately, actually, I'll just go ahead and do that. This is going to be 10 to the minus 14 divided by 1.8 times 10 to the minus 5, which is equal to, type that into my calculator, and we get 10 to the minus 14 divided by 1.8 times 10 to the minus 5, and that is 5.6 times 10 to the minus 10. So very small. That's approximately 10 to the minus 9 if you round that up. So it's still a very tiny number. The water dissociation reaction, since that's the other major species, you have another one that's water. And similar to before, this reaction will be insignificant because the Kw is so small. So far, the, well, actually the K for this particular reaction, let's write it beneath instead. So going left to right, this one is 10 to the minus 14, but here going left to right, so I'll just say left to right, is just going to be 1 over the Ka for ammonium ion. Since this direction is the acid dissociation, we would actually get 5.6 times 10 to the minus 10, so the inverse of that. And so I'm just going to write approximately 10 to the 9th power, positive. So that's huge. So already we can see that 2 is definitely not the major contributor to what happens when you add H plus to ammonia. And number 3 is when chloride ion, since that's the conjugate base of HCl, we add that to water. Since that's the last major species, this is the last reaction that's going to be considered. And this is going to give HCl aqueous plus OH minus. Now you might say, well, yeah, this could definitely influence things if Cl minus is in solution, but the problem is that Cl minus is such a weak base that you won't get any of these things over here. Because the Ka for this is infinite, that just means the Kb, which is just the definition of this reaction going left to right, is effectively 0. It's approximately 0. So it's 0, which is even less than that. But this guy is huge. It's like 1 billion. So the obvious winner is reaction 1. And so that reaction, let's go ahead and carry out that reaction. And that's the titration reaction, H plus ammonia. So let's go ahead and do that. Okay, so this is the neutralization reaction. We can go ahead and rewrite that one down here. Ammonia plus H plus aqueous. In principle, we can write it both directions. We get NH4 plus aqueous. Now, initially, change equilibrium. Initially, the amount of ammonia that we have is 0.400 x, and the amount of H plus that we have initially is 0.060 molar, and we don't have any of this to begin with. So we're not allowing that to equilibrate up to this point, since we're just titrating this. So now at this point, well, we recognize now that we know this reaction, the equilibrium constant, is 10 to the 9th. So effectively, this is an irreversible reaction. It goes all the way to the right. And so, since the part of this problem, we're trying to count the number of ammonias that we have by titrating it with H plus. All we care about is what's going to happen on a major level. So if we compare 1 billion to 1 billion and 1, we don't care. That will just be lost in the details. So what that means is that all of this H plus is going to react with all of that ammonia. So we're just going to subtract off 0.060 from both sides, and we get at equilibrium, both of these are going to be completely zero. Because at equilibrium, H plus is the titrant. It has consumed fully all of the analyte. The analyte was the ammonia. So we have an equation here. Well, and this one is going to be plus 0.060, and so at equilibrium it's going to be left with 0.060. These are both going to be fully consumed if we do this reaction to completion, and we also have an equation now. 0.400x minus 0.060 is equal to 0. So we can just solve for x that way. And we have 0.06 divided by 0.4, and that's 0.15. So x is 0.15, and the starting ammonia concentration of the analyte solution is 0.15 molar, and that's the reaction to the answer to the first part. Now the second part, we're looking for the pH. I know we've done a lot so far, but we've also gone over a lot of the concepts, and the problem-solving strategy is more important. And after, you can compress this down. And I'll show you exactly how to do that. So the next part is to determine the pH at the equivalence point. Okay. So the pH looks like we've scaled up in size here. So the next part is to determine the pH at the equivalence point. Well, we're already at the equivalence point, and the next thing to consider is, well, I know that this reaction, we consider this as going to completion, but in reality, the ammonium ion, it still has a finite Ka value. The Ka value is like 10 to the minus, well, we already calculated it. Ka for the ammonium ion is 5.6 times 10 to the minus 10. So approximately 10 to the minus 9, which is tiny, but it's not insignificant for the purposes of calculating a pH. For counting H plus ions, yeah, pretty much insignificant. But at this point, it's asking us to calculate the pH. So we use this. This is what's left over. And now we allow NH4 plus to equilibrate in water. And that's the last step. So we are going to equilibrate the remaining NH4 plus in water. And it's not going to equilibrate much. You know, one 1/100,000th or 1/100,000th of this 0.06 is going to go back to ammonia. So very, very tiny amount is going to go back. But on a pH scale, since it's a log scale, we're going to be able to detect that. So let's go ahead and do that. So I'm not going to go through the major species or the reaction, since it's the reaction that we're going to do is this. Ammonium ion aqueous is going to dissociate into H plus and back to ammonia. Now I'm anticipating that this isn't going to go very much to the products. It's heavily favored over here because the equilibrium constant, as we've already determined it to be, is, what did we say, 5.6 times 10 to the minus 10. Tiny, tiny, tiny. So there's about 1 billion times as many molecules of that as there are of either that or that in the solution. But let's make that more quantitative. So we have molarity. Everything on the table is in molarity or molar. We write our ICE table. The initial concentration, well, there's the initial concentration of ammonium ion, 0.060, and there's 0 of that. In principle, at equilibrium in water, it could have 10 to the minus 7, but we're effectively considering that to be 0. And we've already consumed all of the ammonia from the H+. So we're left with 0 over there. So we don't have any of that currently. We're going to change this. We're going to use Q for the variable. The only direction for this to go is to the right, even though we anticipate it's going to be a minuscule amount. So we subtract off Q, we add Q here, and we add Q here. That's just based on the stoichiometry of this reaction. At equilibrium, now think about this carefully. If Q is going to be really tiny compared to that, because of the equilibrium constant being so small, at equilibrium it's effectively going to be the same here, because 0.060 is so much larger than any tiny, tiny number that we subtract off. So that's approximately. And here is going to be Q and Q. And if we write the equilibrium constant, 5.6 times 10 to the minus 10, and then the law of mass action for this, we're going to get the law of mass action. Well, we have Q for H+, concentration of H+, and we have Q also for the concentration of ammonia as it re-equilibrates, divided by, well, 0.060 molar, since that's approximate. Now at this point we just solve for Q, so we multiply both sides by 0.060 times 5.6 times 10 to the negative 10, and then we take the square root to solve the quadratic. Square root, answer, and we get that Q for the H+ concentration, since we're looking for the pH, is equal to 5.80 times 10 to the minus 6 molar. So that is the concentration of the H+ ion at the equivalence point. And notice we've just allowed the last little bit to re-equilibrate for the purposes of calculating the H+ concentration, and it actually is really tiny. So it's 1/1,000,000th of a molar, or 1/100,000th of a molar, which is small, but when you calculate the pH, it actually is some value. So let's go ahead and do that. Negative log base 10 of the concentration of H+ ion will give us the pH. Remember, the pH is just another way of counting the number of H pluses you have in solution. It's just a logarithmic scale. That's all that is. So when we do that, we get negative log 5.24. Actually, 5.237. When we do this, we have to add one more significant figure. So 3 instead of 4 now. All right, so that is the pH. And we are done. The last thing I wanted to bring up was the following. Okay, so there's 3 key notes here. There's 3 key notes that I want to go over on these types of problems. And this will heavily, heavily compress this. Obviously, it's taken a long time, but I went over a lot of the details, and I did not compress anything. So the first key point is that all strong acids and well, I'm not going to write and strong bases will fully dissociate in water. That's just the definition of something being a strong acid or a strong base. It just means that it fully dissociates, or that its Ka or Kb is effectively infinite. It's much, much greater than 1. Okay, so the example would be if I have 0.1 molar HCl, then I know I automatically get 0.1 molar H plus and 0.1 molar Cl minus in solution directly right off the bat. So instead of doing all that stuff in the beginning, we could have just written this because we know that this is a strong acid. The second point is to allow all heavily favored reactions. So in the direction that they're written, left to right, heavily favored, where K is much greater than 1, to go to completion. So to consider them as irreversible reactions that just go all the way to completion. So you consume all of the reactions, or basically a limiting reaction problem. First, and then, and usually that might be to consider just counting of atoms, like if you're titrating something. And then the last little tiny bit, the last like tiny little decimal place that nobody cares about when you're counting atoms of other things, then you can consider what's left. So then consider the re-equilibration reactions from that perspective. Okay, so that's like we did with the H plus. The H plus with the ammonia, we assumed it goes to completion for the purposes of counting the ammonia atoms, and then we said, well, an ammonium ion is still it's a weak acid, so it's still going to give us a tiny bit of H plus, about 10 to the minus 6. So we then consider the re-equilibration from the perspective after doing the complete reaction to completion. Third key is the water dissociation reaction. The OH minus, or the OH minuses and the H pluses concentration is only relevant if the concentration of your acid is small, like 10 to the minus 6 molar, and or the acid dissociation constant for that particular acid or base happens to be really tiny. You know, less than, I don't know, 10 to the minus 10. So if you have a combination of those two, that's then and only then do you need to consider the water dissociation reaction, because other times it's just basically comparing 1 to like a billion. So you need these two things, one or both of these two things, to be really, really, really small. There's two key skills that we've developed in this type of problem, and this is really in chemistry in general. Two skills. One is what I call storyline sequential thinking. So that's basically breaking the problem down into bits and pieces in a way that we can get from A to B to C to D. And this is really from the perspective of the molecules involved. So you have to sort of throw yourself into the world of molecules and consider sequentially what's going to happen at each step. If you add something into solution, take a snapshot and say, hold it before this reaction happens. What do I have? Then let the reaction happen. Then consider another beaker. Consider the initial, take a snapshot, allow the reaction to happen, and then add both things together, and then what happens. That's what I mean by storyline sequential thinking. the perspective of the timeline perspective of the molecule. The other one is really IDing the major players in producing one particular species or chemical. So for instance, if you're looking for the H plus concentration to calculate the pH, you're going to look at the reactions that will produce those. And so you're looking at two things. Number one, what are the major species? Because they're in high enough concentrations, if they are involved in a reaction, they're going to cause the greatest change in that H plus. So you're looking for the major species, and you're looking for the most important reaction involving one or more of those major species. Okay, so this is sort of like a Venn diagram. First, you determine the major species and then identify all the reactions, but really we're identifying usually just one reaction that dominates them all. There will be cases where you have to consider two at the same time, but most likely not in an introductory level, college level chemistry class. So you identify the major species, might be 2, 3, 4, whatever, and then the most important reaction will involve at least one of those major species, which will cause the greatest change to the thing that you're looking for. And so you identify that's the reaction that's going to determine my H plus. Okay, and with that, I just wanted to reiterate what some skills that we developed in this problem. The first thing that we did was we deconstructed the problem by underlining and circling important information. And then I've outlined my problem-solving strategy where we separate the goal from all the other information, and then we strategize using what I'd like to call like a mind map, where we're drawing little jumps from one piece of information that we're given to related information that we know from what we learned from chemistry. And the other couple of things that we've needed to understand, since this is a really complex, probably one of the most difficult problems to solve in chemistry, we talked about 3 keys here. So all strong acids fully dissociate, allow all the heavily favored reactions to go to completion first, then consider re-equilibration from that perspective. The water dissociation reaction is only relevant if the concentration of your acid is small or the Ka is really tiny. And the 2 skills that we've talked about is really thinking on a molecular level and thinking time-wise, like what happens first, then next, and really breaking it apart into as many time steps as possible that will allow you to solve this problem. And secondly, identifying the major players in producing particular species that the problem asks you about, where we identify the major drivers of change and the particular the particular reactions that cause those change, which will involve one of those species. Okay, and with that, I will say goodbye.